Thanks for coming. Today I will have a talk about learning function operators with neural networks, and this is part of my work at the institute where we try to improve or accelerate numerical simulations using techniques from AI. And operator learning is one of the emergent techniques, which is very popular in recent years. And I would like to use this opportunity here to show you the basic concepts, why this is interesting for simulation and in general scientific machine learning, and what are the main architectures, main approaches to do this. Okay, so if you have any questions, please interrupt, because I would like to give you a chance to follow every single step. So that's a short overview of what I planned for today. I will start with a short introduction, in particular, what is scientific ML and why it is interesting. And then a large section about operator learning. I will cover architectures like DeepONets and Fourier Neural Operators, and we will discuss important properties of such neural operators. And we will also quickly talk about a new architecture, which is called BERNet. And finally, I will lose some words about software, because at TransferLab, we care about open and accessible software. All right. So let's talk about physical modeling. So actually, we model a lot of different complex physical problems, usually to predict the future, so predict future outcomes, or for engineering purposes. Some examples include weather forecasting, where you see in the image here a hurricane. We want to understand how this behaves to make a prediction about storms, how bad it is, how's the weather next week. But it's also in other domains, like modeling fluid flow is important, or in aerodynamics is important, structural mechanics and electromagnetic fields we can model. We think of, it's also interesting to model sound wave propagation or heat conduction, a lot of such physical processes which have a high relevance, in particular in engineering. And what they have in common is that we have mathematical laws to describe such phenomena. Usually, we use partial differential equations to describe those. I brought one example. So this is an example of a PDE, which is the incompressible Navier-Stokes equation. So we have one equation for the so-called momentum balance and one incompressibility constraint here. So we have two quantities which model the fluid in this setting, where we have u, a fluid velocity, it's a vector, and a scalar quantity is the fluid pressure. And interestingly, writing down such a rather simple formula, I mean, depending on the background where you're from, if you're familiar with this or not, but it's rather simple compared to the complex phenomena it models. So here's an image of a vertex street. So imagine a river with a bird's view, where we have from the left fluid coming and there's an obstacle, and then this flow produces such a vortex street. And this is completely modeled by these short mathematical expressions. And traditionally, in scientific computing, we use numerical methods, such as finite element methods, to approximate solutions to such systems of PDEs, usually with the purpose of modeling such a system. You can imagine we have an airfoil and the flow of air around the foil, and we want to optimize it, so we want to model different scenarios. But in recent years, machine learning became much more prominent, and also with a purpose to such applications. And as probably most of you know, machine learning develops statistical algorithms that learn from data. And thus it is able to perform tasks without explicit instructions. So a recent example regarding physical modeling is GraphCast. It's a graph neural network developed by Google DeepMind, which was trained on decades of historical weather data to predict future weather, so for weather forecasting. Here's a visualization of some of the states. It can roll some future forecasts. And interesting is with this, so it's a recently published science paper, is that this machine learning model outperforms traditional methods in speed and in accuracy. With traditional methods, we mean numerical schemes that use partial differential equations, which were formulated to model how weather and wind on the planet behaves. And these are computational very expensive, so it's not surprising that it's faster, but it's also more accurate. So machine learning has gained a lot of prominence to model physical processes as well. And this is where an emergent discipline arises, which people call scientific machine learning, or SciML in short, which is basically the mixture between scientific computing and machine learning. It doesn't mean that machine learning or other machine learning is not scientific. It's just scientific computing, where we have numerical schemes to solve usually partial differential equations together with machine learning. Some examples of this are physics-informed neural networks, where we use neural networks and incorporate PDEs into the training loss, for instance, pins in short. Or there are machine learning accelerated simulations in any way. But we can also use machine learning for scientific discovery. For instance, take data and try to derive mathematical models using symbolic regression or stuff like that to discover new fundamental laws. But it's also interesting for surrogate modeling, or one part of this is neural operators, what we will talk today. But all of these methods are kind of on this axis. So consider we have data of a process, for instance, and we have knowledge about the underlying physics. And all of the small methods are somewhere in between the small data regime, where we have small observation data, but we have a lot of understanding of the underlying physics. And on the other hand, we have regimes where we have a lot of data, for instance, in the weather modeling scenario, but we have no underlying knowledge of the physics, or limited, or we don't include it. So on the right-hand side, we have the pure machine learning, just data-driven. And the left-hand side, we have the scientific computing regime, where we have explicit physical laws, but no measurement data incorporated. And scientific machine learning is everything in between, where we try to combine methods from both. Note that physics-informed machine learning is a subdiscipline of this. So for instance, incorporating PDEs into the training loss of neural networks, but scientific machine learning also includes other approaches. But this is kind of what we're focusing. All right, so this is where we are. And now I would like to shortly introduce the concept of operators and why this is relevant for this regime. So function operators in mathematics are function mappings. So these are functions of functions. So it's a mapping that takes an input function, like a sine wave, for instance, and maps it to another function, like a cosine wave. So functions of functions. For instance, some examples. The gradient operator, we usually abbreviate this with a nabla, where we plug in a function, computes the vector of the partial derivatives with respect to all spatial coordinates. This is an operator, as it maps of input function u, let's say it's defined on RD, it's a scalar function, to the gradient of u, which can also be evaluated at any point of our domain, but which maps to a gradient, so a d-dimensional vector. So this is an easy example for an operator. But in scientific machine learning, they're much more complicated and more interesting operators. For instance, if we want to solve Navier-Stokes equations, usually we employ some time stepping. And for the momentum balance equation, it could be something like the velocity in the next time step is some function of the velocity in the old time step, un, where this operator g can be derived from this momentum balance equation, where we just replace the time derivative of u by a finite difference, so un plus 1 minus un over delta t, and reorder the equation such that un plus 1 is on the left-hand side. This is usually what traditional schemes also solve for, but imagine we can learn this operator to predict, given an old time step, efficiently the next time step of a system. And this is why operators are so interesting in scientific machine learning. They are omnipresent. That's not only derivatives, but there's also much more complicated operators like this operator here. And the interesting thing is that neural networks can learn operators. And we will have a look how this works and why, or how this performs, what specific properties of these approaches are in the next section. Before I dive into the mathematics, are any questions up to this point? I don't think so, because it was just the introduction. So let's continue with some more mathematical details. Okay. So let's first clarify what an operator exactly is. Okay. So let's assume we have two function spaces, a function space U and V. These are Banach spaces of functions on bounded domains. So elements of U are functions that map a domain D to some other domain. And these are Banach spaces. So imagine vector spaces, but with a metric of functions. And an operator is simply a function or a map which maps this function space U to a function space V. And if we now want to talk about operator learning, then what we mean is the following. Suppose we have a set of observations, so UI, VI, where UI is some function in the input function space, and VI is the mapping of UI of this operator. Maybe distorted with some noise, so that's why here it's an approximate. And operator learning now is the task of building a parametric map. I call it G theta, which also maps from U to V, with a set of parameters theta, some p-dimensional vector, for instance, like a neural network, that minimizes the following empirical loss. So the minimum over all parameters, then the average over all our samples, all our observations, and then we have the norm of the function V and the mapping of U using this parametric map. And note that this is a norm in function spaces. So VI is not a vector, it's a function. So we use the norm here defined on the function space V. For instance, an L2 norm, something like that. And that's the goal. We would like to build some parametric map that acts on these function spaces such that we can map the functions. And this is what we call neural operators. There's one specific framework which many people refer to as neural operators, but I want to call everything which maps functions or which approximates operators with a neural network. I call this a neural operator. And this is a non-exhaustive list of some of the relevant architectures. For instance, the first one of these kind of architectures was DeepONet, which was proposed in 2019. The Nature paper was published in 2021. There's a second very prominent architecture for Fourier Neural Operators, which was published right after that one. And then there is a bunch of other architectures. For instance, POD, DeepONet, multiple input-output network, BellNet, graph neural operators, multiple graph neural operators, Laplace neural operators, and so forth. So there's a lot going on, a lot of different things arise in recent years. And these architectures try to mimic or try to solve the same problem, but they differ in the motivation, how they are derived. They also differ in their performance, depending on the task we try to solve. And they also differ in very, very important properties regarding operator learning, which we'll cover later. As I don't have time to cover all of these architectures today, I will just focus on the most important ones. So we will start with DeepONets. We will cover Fourier neural operators and the way there we will handle graph neural operators, and then I will comment on BellNets as well in the end. So let's start with DeepONet, which was, as far as I know, the first architecture which proposed a concept like this. So a DeepONet, which is a short version of Deep Operator Network, or other papers cited as DON architecture, is directly motivated by the universal approximation theorem for operators. And this theorem is described by function evaluation. So this is one of these things, how you can represent a function. You probably might know the universal approximation theorem for neural networks, which says if you have a two-layer multi-perceptron and you have enough of neurons, then you can get an arbitrary precision. And this is the same theorem, but for operators. And before I show you the theorem, I would like to visualize how it maps functions, how this is represented. And the question already was regarding the training data. So let's say we have an input function U. Then the theorem is formulated in a way that it evaluates this function at a set of fixed sensors. So positions x1 to xm, like here, this is one function evaluated at this sensor position x. This is another function evaluated at the same positions. And our operator g maps this function to the output function g of u. And as this theorem is formulated, we can then evaluate this output function at some random location y. So some point here or here or here. Okay, so the representation of the function is by a list of evaluations. All right. Okay, so this is from this paper here. As I said, Nature paper 21. We also written a pill about this. And this theorem looks like this. I would like to take 2 minutes to understand the slide because I think it's kind of interesting to understand this in more detail. As I said, this is a similar result to this other universal approximation theorem. And this was proven as well by Chen and Chen already 1995. It's just that this theorem has been rediscovered and reused because it's so interesting to use operator mapping for scientific machine learning in this regard. So the theorem states, suppose that there's a sigma, it's a continuous non-polynomial function. That's what we usually refer to as activation function. So nothing special. Then we have some spaces. X is a Banach space. I called this V previously. Then we have some compact subsets. Nothing too important here. And V is another compact set in the continuous functions of K1. K1 is a subset of this Banach space. So G, the assumption for G is that it's a nonlinear continuous operator which maps V is the input function space, into another function space. Here it's the function space of continuous functions defined on this compact subset K2 of RD. So now the statement is, for any epsilon greater 0, there exist positive integers, constants, this is usually what we refer to as weights in neural networks, and positions xj in this K1. K1 was the definition domain of the input function space, such that we have the following estimate for all u in our input function space and all evaluations in the output function space definition domain. So this is where x comes into play. X is, the statement says there is a list of x where we have to evaluate our input function u, and then we also have some weights and some connection like this, such that we can approximate the mapped function in every coordinate y with a desired accuracy. So there's no strong relation between y and x. It just says if you want to have a specific accuracy, you can find a set of these weights and positions where you have to evaluate. And actually, so that was the motivation to introduce DeepONets. And if you have a deeper look into the structure of this formula, you can observe that this is the structure of what we usually refer to as multi-layer perceptrons. For instance, here in the part, we have these function evaluations at the finite set of x's. And then we have a linear map. So it's a linear layer and an activation function applied to it. We multiply some constant, okay. And the second part is also a linear map in y here, also with an activation function. So, and this is a product summed over all indices k. So basically we have two vectors here. The first part, which they call branch, and the second one, which they call trunk, because the second part is only dependent on y, and the first one is dependent on u of, or on u, basically. And then this is a scalar product of these two vectors. And that motivates to have the following architecture. So it's directly motivated from this theorem to separate a DeepONet into two networks. The first one gets the input function u, evaluates this as a set of sensor positions, puts them into a branch network. In the theorem, it was a simple linear layer with activation function, but in general, it can be any neural network with universal approximation properties, and you get a vector b1 to bp out of it. The second one is we have a y, the coordinate y, which enters a trunk network, which was also a simpler network, but it could be a general neural network, which gives you this vector of t1 to tp. And then you make a scalar product, and then this sums up to an approximation of the operator evaluated in u, evaluated in the coordinate y. And if you see this from a function space perspective, you can observe that it's essentially the trunk network, which learns basis functions, and the branch network, which learns basis coefficients, because this one is what depends on y, and the other one gives you the coefficients to plug in your basis functions together to represent this function on the right-hand side. So that's a basic DeepONet. There are several extensions, but with this simple DeepONet, we are already able to do pretty cool things, because we can input a function and we get out another function. So what if we consider the following problems? And what we aim at is building a physics-informed DeepONet. So for an example, consider a Poisson equation in 1D, which is minus Laplace u equals some source term. Laplace means the sum of the second derivatives of the function. We just consider simple domain and usually zero boundary conditions. And now let's say our function f, the source, is from some function space. For instance, the function space of third-order polynomials. Now the question is, or the answer is, we can learn the solution operator of this partial differential equation system. The solution operator maps the source from f to u. Here's an example. Here's a representation of 3 of these polynomials. And these f's map to a function u, which is the solution of this PDE. For instance, consider the yellow line, which is positive on the left-hand side. Here's the 0 and negative on the right-hand side. And as the second derivative equals f, it basically means the curvature equals f. So in this area, we have a positive or negative curvature, and the curvature sign changes from this point on. And that's exactly what we see here. So positive curvature, negative curvature, and 0 boundary values. And that's very interesting. So this is a common setup we have in scientific machine learning or in solving partial differential equations, where we can parameterize our PDE in some regard here in the source term, and then learn the operator to map this parameterization to the solution. And here we can actually also learn this in a physics-informed sense, because we can evaluate a function u in any point we would like, and then we can incorporate a physics-informed loss and train a network to solve this PDE, actually. And usually that's much, much more faster than using a classical solver. Maybe not for this problem, but we will come to similar problems later. Okay. So that's what I would like to share about Fourier Neural, about DeepONets. Let's come to another architecture. I think I have to speed up a little bit because there's still some things I would like to cover, but yeah, let's continue. So the second major famous operator architecture are Fourier neural operators, or neural operators in some regard. And they follow a completely different way of construction. Let's have another way to look at function mapping. Let's consider the integral kernel operator. So assume we have some kappa, which is a continuous kernel function. That means it maps the product space of 2 domains to a matrix. And then an integral kernel, k, which is defined like this here, maps an input function u in this way to another function v. So k of u is just the integral of this kernel times this u. And as this is still dependent on y, the right-hand side is a function in y. So essentially, this kernel maps a u to a y. And these can have different domains of definition. But if we assume that these are the same, and we assume that the kernel function is just a kernel function in the difference of x and y, then k is actually a convolution. So we can write k by the convolution operator. That's nothing new. So this operation of integral kernel operator and convolution is well known. It's broadly used, for instance, in convolutional neural networks or for fundamental solutions of PDEs. And interestingly, this is the main building block of Fourier neural operators. The neural operator framework outlined by Kowalski et al. Here's a recent paper with a large overview, extensive overview of this framework. They try to mimic the framework of a usual deep neural network. And it looks like the following. Consider an input function A, then they apply some lifting procedure. It's nothing special, just increasing the dimensions of the hidden representation. So like adding some channels in a convolutional neural network. And then they have an iterative kernel integration until they project the output to the function U. And every one of these hidden layers is essentially taking an input function and applying such an integral kernel operation, adding some bias, multiplying some weights, and applying activation function. As we know this from hidden layers in deep neural networks. But the interesting thing is that we work on functions here, and we incorporate this integral kernel operation within each layer. The question is now how to represent this integral kernel operation and how to do it efficiently. So the parameters of such a neural operator are, of course, the weights here and the bias here, but we can also parameterize the kernel, as it is done in CNNs, for instance. So the question is, how do we choose such a kernel function, which depends on some parameters, to evaluate this integral efficiently? Because if you imagine we just sample points in the domain D and the same number of points in D prime, then we would have a complexity of J squared, because we have to evaluate for all the points the integral, and the integral means for all the points. So that's bad. The question is, can we do better? The most simple idea you can have is use truncation. So the idea is just to integrate over a subset, let's call it S, dependent on a position Y of the input function's domain. For instance, a ball with a radius R. Then this integral kernel operator becomes integral over the subset. That might be faster because the subset might be 100 times smaller than your whole domain. But still, as you sample more points, the points in the subset increases. So asymptotically, you'd still have a complexity of J squared. Another idea is what is called graph neural operator. It's similar to graph neural networks, where you have a discretization of your domain, let's say a finite number of points, y, 1 to yj, with neighborhoods. For instance, think about a mesh discretizing your domain, and these are the vertices of the mesh, and the neighborhood is all the vertices connected via edges of this mesh. Then we could also approximate this integral by just computing the mean, the average, over this neighborhood. And if we assume the neighborhood is smaller than some absolute value of n, then this would reduce the complexity. But on the other hand, it makes it more complex because we have to build a graph, and we have the problem that the graph introduces some locality. So like the communication steps in graph neural networks, you would have to communicate several times. You're not able to capture global effects anymore. That's one special case. 1 second, then I give you a chance. Just to note, the convolutional neural networks are a special case of graph neural networks. So if you choose a specific discretization, like a grid, the neighborhoods are your stencils, for instance, 3 times 3, and your kernel is then as discretized in a CNN, then this is a CNN. But this is just a more general form and formulated in a continuous setting. There are more effective ideas, and that's where Fourier neural operators come into play. Okay, so now let's talk about the F in FNO. So the idea here is to represent the kernel operation in Fourier space. This was presented on an ICLR 2021. So we have to make some assumptions, but let's assume the input domain and the output, so the input domains of both functions are the same, and we have complex valued functions. And we denote by F the Fourier transform and F minus 1 the inverse Fourier transform. So now assume we have a kernel which is like in a convolution, just dependent on the difference. Then our kernel operator becomes the convolution. And now, applying the convolution theorem, that's a theorem, a result for Fourier transform, it gives us that we can write this convolution like this. So mapping both functions in Fourier space, and then just apply a dot product between those two, and then transform back. And this approximates the integral on the whole domain. So it's not local anymore. And you can evaluate this pretty efficiently. In particular, if you use fast Fourier transform, you can also use the Fourier transform efficiently. Then it's just a dot product and the inverse fast Fourier transform. And what we also can do is we can directly parameterize f of k phi in Fourier space. So just let's replace this by some matrix, complex valued matrix. And then this is the Fourier integral operator. And if we use FFT, so fast Fourier transform, this has a complexity of j log j and does not include any assumptions on locality. But of course, we have some assumptions to perform the Fourier transform efficiently. Here's an example. This is one result of this paper where they predict the next time step of a turbulent flow. It's the operator I showed you in the introduction. So we have some initial condition. The vorticity is printed here. And this is mapped over some time step through some flow field. This is the ground truth. They used some classical numerical spectral method to solve this. And this is a prediction by the trained Fourier neural operator. This looks a little different, but pretty well. The interesting thing is that because FFT and things like this are so efficient, the prediction is orders of magnitude faster. It's like 10,000 times faster in comparison to the traditional method. But as we have to make strong assumptions, it's restricted to a unit square with periodic boundary conditions, such that we can perform the FFT efficiently. So what's now the difference between DeepONet and FNO? There was one benchmark study published in 2022 in Computer Methods in Applied Mechanics and Engineering. The author was Lu, so this is the inventor of DeepONet, but it was peer-reviewed, the paper. What the conclusion was, so they benchmarked a lot of different problems of these kinds of type, like solving PDEs, parametric PDEs. For instance, here, this is a solution of a Darcy flow in a triangular domain with some cut here in there. Then this is a true solution, DeepONet, and some modification of Fourier neural operators to handle these kinds of shapes. And what they found is the vanilla methods, as I've presented them to you, may lead to suboptimal results. But if you use some proper extensions of both methods, and they introduce a lot of them, then both operators exhibit the same accuracy for the same size in terms of parameters. So no real better or worse here. And what's also interesting that some architectures are more flexible in terms of problem settings. And we want to talk about this in more detail in the following. Some important properties of operator learning are that we map functions to functions. And we want to do this because we want to be independent of the discretization. So if we already discretize our domain by a mesh and we map the solution on the mesh to the same mesh, we could not input any other mesh. So one important property of this whole framework is that we are discretization invariant. So this means the locations of the sensors in the input function domain, that they don't have to be fixed. So for instance, we have one function, sample one, evaluated at these positions, and another sample evaluated at different positions. That's important if you want to input unstructured data, a function represented by a mesh, for instance. A second interesting property or important property is to be prediction-free. That means that the discretization of the input can differ from the discretization of the output. So we want to input a function, evaluate at some points, but we would like to evaluate the function, the map function, at some arbitrary other positions, like here. This enables things like physics-informed training or even super resolution, where I show you an example later. And finally, another important property is domain independence. that means that the output function domain is independent from the input function domain. For instance, you can map a one-dimensional domain to a two-dimensional domain of the output function. That's much more flexible. For instance, you can map a function as boundary conditions to a solution on the full domain. And if we have a look at the architectures I've shown you so far, then they actually have pretty different properties. So for instance, a DeepONet, or in the table DON, is not discretization invariant. As I mentioned, we have the set of input position x1 to xn, but they are fixed if you train the neural network on these positions, so you're not able to input a function evaluated at different positions. In contrast, a Fourier Neural Operator interpolates your function, kind of, by transforming it into the Fourier space, and so it doesn't really matter where you want to evaluate your function. But on the other hand, the DeepONet is prediction-free. You get a continuous function as an output. You can evaluate wherever you like. But the Fourier Neural Operator is not prediction-free, as you have to have the same input mesh and the same output mesh to perform the Fourier transform accordingly. And the same applies here for the domain, where Fourier Neural Operator is restricted to the same input-output domain by the assumptions we had to make. And because I'm running out of time, I will skip the presentation of Belnet. Belnet is just a recent paper from 2022, where they propose a generalization of DeepONet, which actually is able to fulfill all of these properties. And I just want to show you that these architectures differ in very important properties for these kinds of settings, and people are investigating this. I will skip this, but the general idea of Belnet is to incorporate also the positions where you evaluated your function u, and use this to construct a function space where you can project u into. And as you also include these functions, it becomes discretization-invariant DeepONet. But the interesting thing is also that this is also special, or Fourier neural operators are also a special case of this. So all things are linked together, kind of. And yeah. One final controversial question is, if you talk about neural operators, is the question, is this just interpolation? Because, I mean, if you want to map a function, you can always interpolate a function into a finite dimensional function space. It means discretizing it, for instance, in a polynomial space or in a piecewise linear space. And then you have a finite list of coefficients, which you could map with a neural network. And Fourier neural operators, at least at their core, they use the Fourier transform. So this is basically interpolation. You just interpolate to another space, then you have some parameterization of these parameters, and then you map back. Belnet, as shortly shown, learns an interpolation. So this is more general, but it's still kind of interpolation. But it does not interpolate and interpolate back, but it gives you a continuous output. So something in between. And for DeepONet, it's, I think, less clear. It's not clear if it's interpolation or not. It's some kind of interpolation by function evaluation, but it's still no interpolation back. Let's do this quickly. We care about software at TransferLab, so I would like to give you a list if you want to try out neural operators or operator learning. There are some frameworks available. One of these is DeepXDE. It's developed by the inventor of DeepONets, which is a framework for physics-informed machine learning, implementing DeepONets and physics-informed DeepONets. It's a Python framework with several machine learning backends. And then there's Neural Operator. It's a framework by the inventors of these neural operator frameworks, and in particular, it's the official implementation of Fourier neural operators written in PyTorch. But there's also Modulus by NVIDIA. So these guys are kind of related to the NVIDIA efforts here. Modulus is more a deep learning pipeline framework for physics machine learning, and implements also Fourier neural operators or extensions like spherical Fourier neural operators. And then there's also a library, SciML, which has a package neural operators.gl. So it's written in Julia. These are the developers, in particular, Chris Rackauckas is at MIT, very, very prominent researcher there. And they implement DeepONets, Fourier neural operators, and extensions as well. And then there are a lot of smaller frameworks like Torch Physics and similar ones. And just To make a shameless self-plug, we started with the development of continuity to establish a high-level library for operator learning with neural networks. And these frameworks, they differ kind of in how they represent functions and what they are able to map. And we want to establish a unified operator framework. We have the following signature. So a function v evaluated in coordinates y should be represented by a neural operator, which gets all these input information, x, u, and y. For instance, in DeepXTE, the DeepONet only gets u, and other frameworks differ in this way as well. And we would like to implement various neural operator architectures in this. We also want to include TDEs for physics-informed training, and then add expressive benchmarks, because it's important to compare those to see how they perform and which properties they differ. And finally, one example of super resolution. Neural operators can use super resolution because they map to continuous functions. So here's an example from a Flame AI challenge, where the task was to upsample images from 32 resolution to a higher. And this is where we trained a DeepONet, taking these 256 input values and map this to a continuous function output. And then you can sample it whatever you like at the target resolution or even finer. There's also a recent paper, a super resolution neural operator, and in this Flame AI challenge, the first position, so the most successful solution was actually using this super resolution neural operator. So for image processing, this might be interesting as well. And so, short summary, neural operators transfer the concept of mathematical operators into machine learning. They have gained a significant attention in recent years, and there are many architectures with various characteristics. What we always want is discretization-invariant, prediction-free, and efficient neural operators, and architectures differ here and there. So despite open questions, neural operators have already exposed a lot of promising results, but still some work to do, and I think exciting times ahead. And with this, thank you for your attention, and I'm looking forward to take some questions.